welcome back. So, we were talking about heat of formation of ions. So, this is going to be the last lecture on energy balance with chemical reactions, right, and we are going to talk about a very interesting case or heat of mixing, right. And after that only one topic remains, and that is humidity, and which we will cover in sort of 4 lectures. So, we were continuing our discussion with the concept of heat of formation of ions. So, let us have a look into it and first finish it, and then we will move on. So, I think by now it is clear to everyone that the combined heat of formation from this formalism that we talked about, which essentially combines Hess law, nothing else, another application of Hess law you can say, the formation reaction or the combined heat of formation of H plus and OH minus ions is considered is minus 54.957 kilocalorie. Now, at this point some more assumptions. We assign that the heat of formation H plus ion is 0. This is an assumption, right. So, if you make this assumption, then immediately what follows is the heat of formation of OH minus ion, right, is equal to minus 54.957 kilocalorie, right. So, again what you must remember, just like the steam table had some fundamental basis, right, you must remember that whenever you are talking about the heat of formation of any ion, that actually rests on this very, very interesting and very, very important fundamental assumptions. So, let us see what we can do. For example, so now we know that the heat of formation of OH minus ion is equal to minus 54.957 kilocalorie per gram mole, right. And we also know the heat of formation of sodium hydroxide in aqueous state is 112.236 kilocalorie, right. Now, what does this mean? What is the formation reaction of NaOH? The formation reaction of NaOH is going to be sodium in solid form plus half oxygen in gaseous form plus half hydrogen in gaseous form, leading to NaOH. So, this is the formation reaction, and this is the heat of this particular reaction actually, right. Now, again we know that NaOH, following Hess law, one can write in aqueous medium, gets dissociated into Na plus and OH minus aqueous, right. Okay. So, then what one can argue? What one can argue that combining these two, one can argue that the heat of formation. So, what are the things we know from this particular reaction? We know that the heat of formation of sodium hydroxide is known. This is known, and heat of formation of OH minus is known, right. So, if these two are known, then it is logical that one can find out, following this approach, the heat of formation of Na plus, which turns out to be this is minus 112.236 minus of minus 54.957, and which is minus 57 0.279 kilocalorie per gram mole, right. So, this is again how you can go ahead. So, this is more of a concept, as I told, this is a hypothetical concept, but an important concept and you should know it. This is how you can go ahead and keep on calculating the heat of formation of ions. But whenever you see the heat of formation of any ion, and following this approach, you can keep on now calculating the heat of formation of more ions. So, for example, you can know the heat of formation of sodium chloride, and now you know the heat of formation of Na plus. So, that way you can find out the heat of formation of Cl minus also. But that you must remember that whatever values of heat of formation of any ion you report, that actually rests on this particular assumption. Okay. So, that is what I wanted to talk about heat of formation of ions. Now, let us move on to another interesting topic, which is known as the ideal solution, right. So, what is ideal solution? We have essentially, up to this point, we have implicitly assumed that any mixture has its properties as its sum of weighted properties. So, let us say we have a mixture of liquids, and we have assumed that the Cp of the mixture is Xa into Cpa plus Xb into Cpb and so on, or let us say the enthalpy of the mixture is Xa into A and so on. So, in all these cases, these mixtures of gases or liquids or whatever we have assumed are non-reacting. Okay. So, there can be different type of mixtures. Of course, I am not going into all the details. So, there can be different type of mixtures. This is a very interesting topic for me. For example, you can have gas mixture. Of course, the best example is air. You can have gas liquid mixture, right. You can have gas solid mixture, and why don't you find out examples of each one of them. You also have liquid mixture, very common, solid liquid, very common, right. Solid of course, again very common, stainless steel is the classic example. So, all these type of mixtures are possible. In fact, one can also distinguish as a gas liquid mixture and a liquid gas mixture, depending on which one is the majority phase. But let us not get into all that. So, any ideal solution, when you mix them, right, mix the different components, there is no thermal effect. It does not involve any enthalpy change. So, for an ideal solution, there is no change in enthalpy, there is no change in enthalpy due to mixing. But in real solutions, they involve change in enthalpy due to dissolution or mixing, right. So, let us understand what they are. So, you can have terms like heat of solution. Typically, this is referred to when a solid, for a solid in liquid type of a mixture. You can have heat of mixing. This is liquid in liquid, and heat of dissolution, there is also another term. It comes from the word something dissolves, right. Now, before I move on to what is integral heat of mixing or heat of solution, let me just tell you something about the process of this dissolution. Let us say we all know that sugar dissolves in water and sand does not dissolve in water. So, exactly what happens? This is a question that you might have been, many of you might have been following from your school days, right, and you give some interesting and funny answers at times, if I am allowed to use the word funny, that the interstitial, the size of the sand particles, firstly this word particle is very vague, is large and they do not get into the interstitial spaces of the solvent like water. It is not like that. Anything dissolves means, so when you take a cube of sugar and put it at the bottom of a container having water, let us say, you see that sugar slowly dissolves. What exactly happens? Something will dissolve when the molecule of the solute prefers to remain surrounded by the molecules of the solvent. So, when you drop a cube of sugar or even a single grain of sugar which contains thousands of molecules, each molecule, they are now initially only in contact with sugar molecules, and there is the energy of interaction between them, which can be van der Waals interaction or whatever, which is known as the cohesive interaction, the interaction between the similar molecules. And when these sugar molecules come in contact with, let us say, the solvent water, now there is another type of interaction that is happening between the sugar molecules and the water molecules. Now, this is called the adhesive interaction, because this is dissimilar interaction, right. So, when the strength of the adhesive interaction, so when the interaction between the sugar molecules and the solvent molecules becomes stronger than the strength of interaction between sugar molecules and sugar molecules or the solute molecules themselves, then what is going to happen? That particular solute molecule is going to leave the cluster of solute molecules and simply go away with the solvent molecules, right. So, this is the concept of dissolution, or in other words, so when sand does not dissolve, it means that the sand molecules do not want to remain surrounded by water molecules. They would like to prefer in vicinity of other sand molecules itself. This is the fundamental physics of dissolution. Why something dissolves and why something does not dissolve. Of course, this can be explained in terms of wettability and number of other factors which I will not cover. And dissolution is something very similar, right, something very similar to evaporation, because what happens in evaporation? You have a liquid pool, so you have a condensed phase, and so when the molecules evaporate, right, so that particular molecule which is taking part in evaporation or which is evaporating, which actually changes phase from the liquid stage to the vapor phase. Of course, there is a distribution of energy, right. So, all molecules in the liquid phase does not have the same level of kinetic energy which we have talked earlier in this course, right. But evaporation is also aimed at breaking down, right, of a condensed structure. So, same is dissolution. So, what I mean by breaking down of a condensed structure, initially you take a bath of liquid, right. So, where the liquid molecules are sort of interacting with each other, and once it evaporates, now the liquid molecules are dispersed, right, in the vapor phase, right. So, typically evaporation takes place between a liquid and a vapor, and dissolution takes place either between a liquid and a liquid or a solid and a liquid. So, for example, when you take even two liquids, you take, in certain cases these two liquids mix intimately, right, alcohol and water, for example. So, what does it mean? So, water molecules do not mind remaining surrounded by alcohol molecules, or alcohol molecules do not mind remaining surrounded by water molecules. But when you take, let us say, oil and water, so the oil molecules do not want to be surrounded by water molecules. The oil molecules feel that they should remain together, and therefore you see phase separation. It is very common to see, if you pour some oil on water, you will see patches of oil on the water surface. So, the oil molecules remain together, they do not penetrate into the bulk of the water phase, and therefore they do not dissolve. I hope it is clear to all of you. Acid and water, for example, it's a perfectly dissolvable system. So it means that the acid molecules prefer to remain surrounded by water molecules. But there is some thermodynamic effect or thermochemical effect associated with such mixing, which we are going to talk right now. Okay. So, so essentially the heat of dissolution or heat of solution is the enthalpy change associated with dissolution of a substance is termed as heat of solution or heat of dissolution. So formally it's something very interesting. It's not exactly similar to heat of reaction, because what you can do is that you can take one species, let's say you can take an acid molecule, and now you add one or maybe you take a mole of acid and then you add 1 mole, and then after it dissolves you add 2 moles. So is there a progressive thermal dissolution or something like that? That is the interesting part of heat of dissolution. So let us first write down what it is, and then I will look into some data and which will make it very, very clear. So there is a concept called standard integral heat of solution. This is a very interesting concept, I would say, which actually says that the enthalpy change of a system when 1 mole of solute dissolves in N1 moles of the solvent with or at 25 degrees centigrade and 1 atmospheric pressure. That is why the word standard pressure. It is known as the enthalpy change of a system when 1 mole is known as the standard integral heat of solution. Important to note, as we will soon see, the value of integral heat of solution depends entirely on the value of N1, right. The asymptotic value, so this we will also see, there is an interesting definition. The asymptotic for n1 tending to infinity is known as heat of solution at infinite dilution, right. And as we have a concept of an integral heat of solution which depends on n1, right. So, we understand that these two values are going to be different. And as these values are different, of course, if you subtract these two values, right, that would lead to a concept of incremental or differential heat of solution, right. So, these are the essential concepts. Now, at this point, let us look into the data set. I am not going to waste time by typing the data. Let us look into one simple concept of dissolution of HCl, right, in water. Or the aqueous solution. So, what we have, the first data, the composition is pure HCl, and this delta H0 is nothing but the heat of formation. Now, when you add 1 mole of HCl into 1 mole of water, so moles of water added is 1, you see the delta H0 for this incremental step is minus 26.225, and the total, so the incremental heat of solution is minus, so this one, and this is the integral heat of solution. Integral heat of solution for delta H S one can write, but N1 equal to 1, right. Similarly, if you now keep on adding more and more moles of water. So, for example, we have data for 2, we have data for 3, you see that the incremental change in enthalpy progressively reduces. Why this happens? Because when you add the first mole of the solvent, it has to actually overcome all the interactions between the HCl molecules to dissolve it. Now, when subsequently more and more water is added, it actually has to overcome far less number of such interactions, because already HCl has dissolved in water, right. So, as you keep on increasing, you can see, so for example, 1, 2, 3, 5, there is some significant values, and then at 50 moles if you add, the value is very, very less. At 100 moles it has reduced to 0.569, 1000 moles it has now reduced to 0.163, right, and infinite is even higher. In fact, you keep on adding where the incremental delta H does not change, that is where you can say that this is the, as we argued in the previous slide or talked in the previous slide, the heat of solution at infinite dilution, right. So, I request all of you to look into this data carefully. So, this is the heat of solution at infinite dilution, and if you are supplied with this data, for example, then stepwise for each step, incremental step, you can also find out. So, if you have the data set for the integral heat of solution, right, for N1 equal to 1, 2, 3, 4, 5, then you can find out from there the differential or the incremental heat of solution for each step. And that is very, very interesting, because what is happening is that you are adding the same 1 mole of the solvent, but depending on the value of N1, the incremental value is changing. So, that is very, very interesting, right. So, this is what is known as the concept of integral heat of solution. So, enthalpy of a solution, so what emerges, this is the last few words, enthalpy of a solution at temperature equal to T relative to pure solute and solvent at the same temperature and pressure. This is essentially the integral heat of solution. Thus, the enthalpy of a solution at temperature relative is expressed as enthalpy of solution equal to N1 H1 plus N2 H2 plus N2 into delta H2S. So, N1 obviously you should understand number of solute moles, number of moles of solute, N2 equal to number of moles of the solvent, and this is the integral heat of solution right. This is the integral heat of solution, and we now also understand that had we had an ideal solution, right, this term would have been 0 for an ideal solution. So, it is very simple. Wherever so you must be knowing that if you are adding acid to water, right, there should be very careful arrangement for cooling, because the reaction chamber heats up, and therefore, you must therefore straight away realize that what is happening is it's a non-ideal solution, because otherwise there will be no effect of heat of solution or heat of mixing, right. So, of course, we write that delta H2S is the integral heat of solution of component 2, that is the solvent, right, at temperature T, right. So, these values again, of course, you can understand that depend on the temperature, but whenever you are talking about the standard heat of solution, right, we are essentially talking about the enthalpy effect at 25 degree centigrade and 1 atmospheric pressure. So, that sort of brings us to the end of our discussion, whatever I wanted or intended to cover in as a part of this enthalpy balance with chemical reactions. Thank you very much for joining, and only one major topic remains, and that is a discussion on humidity, and where I will teach you the use of the very, very interesting psychometric chart. Thank you very much.